Unit 5, applications of derivatives. So my quote is, the point of a math class is to build a person's capacity to puzzle and unpuzzle oneself. Unfortunately, for the vast majority, no, that's not true. For many of you, that will be the lasting effect of calculus, saying, I survived calculus. It was insanely hard. I dug deep into it, figured it out, and got myself back out of the hole. Yeah, this chapter is just as good as any. It's for doing that. It's not the worst one we'll do all year. It's probably ranked 3rd or 4th, but it gets there. So in this unit, we're gonna learn how to figure out the difference between absolute, local, extrema, and understand how to find them. It's kind of a tedious process, but it's not too bad. The mean value theorem is very easy. Unfortunately, people don't get it. There's nothing to get. It's an existence theorem, but we'll get there. Understand that when we look for max or mins or increasing and decreasing functions, how do you do that? Well, it's not that hard, but you always got to watch out for endpoints. They're going to say from here to here, check the endpoint, check the endpoint. There's a max, there's a min. This is smaller, that's whatever. Points of inflections, piece of cake. Derivatives to graph things, which we never really do anymore because we have our graphing calculators. That's not too hard. There's some mathematical business economic problems. I generally don't get into them. They're not on the AP exam, but it's good to see what we're doing this for. Linear approximations, which I find extraordinarily simple, but people just don't get. What's going on if we zoom in really, really, really close on a curve? And then related rates. That's kind of tricky, but at the end of the day, it's not too bad. So one of the early uses of calculus was to find these extrema, these maxes and mins. All right. Not really something we worry about anymore. I distinctly remember doing a whole graphing unit before we got to some of the heavy duty calculus. And we don't do that anymore. I mean, we do a lot of it in pre-calc, but we don't sit down and just bang out graph after graph after graph after graph. So what are the extrema? Well, they're maxes and mins, and we call them either local, relative, or absolute and global. Don't ask me why they do that. So this is going to be a local max, and they've got dumb definitions, but we'll get to that. And this is going to be a local min or a relative min. How come it's not an absolute min? Because you can see the graph goes down further. So this is not the most minimum point down here is. That's not the most maximum point up there is. We can get graphs like this. Now we have a global or absolute max. I'm real loose with my terms. I throw max and min around, so watch me because I'll screw it up. And then these are just relative max min. That's a max, that's a min, but it's local or relative. This is the highest point of the graph, so it gets to be called absolute. You just got to work it out. Again, we usually get these like intervals. We're going to stop here, we're going to stop here. So you have to check your endpoints. Boy, do people forget that. So here's the extreme value theorem. And this is why we got all that stuff from unit 2, continuous, closed interval, and derivative, blah, 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 blah. And it's like the intermediate value theorem. It just says, I got a continuous function, a closed interval, I'm going to have a max and a min. That's it. All right. I've already answered these questions. What's the difference between absolute, and let's give that another name, or global, and local or relative extreme values? All right. I'm going to just say it depends on interval. Let's say, hey, it's from -4 to 4. Something like that. I'm making stuff up as I go along. Well, this is going to be your global max. And this is going to be your global min. All right. This is going to be a relative local min. We're not usually going to call that a local min, but it's a minimum because when we go to the only way we can go to the right, so on and so on. Now, this is very similar to what's going on up here. Closed interval, closed dots, those are filled in. They look like they're not, but let's make sure they are. There's going to be a max, there's going to be a min. There could be two of them. This could have stopped up here and they're on the same line. It's just max and min. So enough with that. What do we know about derivatives at these values? Well, the derivative is 0. The tangent line slope is 0. Derivative is 0. So we're going to do this thing where we find derivatives, we find the zeros, we say, hey, there's zeros at -2 and 3. This is an example. And then we're going to say, well, what's the slope here? Slope is positive. And what's the slope here? Well, the slope is negative. Hey, that, positive, negative, that's going to be some sort of max, local or global. We'll figure it out later. And then, oh, that's going to be some sort of min. So we'll do these little arrows, and I'll show you that in a second. So other points where the derivative equals 0, no, later. And what's the difference between a critical point and a stationary point? Stationary point, it's easy to remember. The derivative equals 0. Critical point, derivative equals 0, or endpoint, or undefined, that sort of thing. So critical point means go check it out, like your endpoints. Like I keep saying, hey, don't forget to check out your endpoint. Don't forget to check out your endpoint. Don't forget. So everybody forgets to check the endpoint, including me. So as always, let's jump right in and get working. To find the min and max and min values of this. Now I'm just going to graph it on a calculator. Be careful, we got an interval here. So we're going to have something like this. And this is going to be our local max. It's going to be our global or absolute max. And this is going to be our global min. And by the way, you're probably like, yeah, that's interesting. Why don't I just graph these? Well, sometimes we can't. Sometimes we're looking at minimizing cost. So we got to, do some math and figure out where the best spot to be, and maximizing profit, things like that. But also notice that the endpoints come into play here without doing any calculus. Don't forget to check your endpoints. Let's do this the calculus way, the way you would normally do it. We would say, what's the derivative? So f prime of x equals 2/3 x to the -2/3. All right. And then we would say, well, x cannot equal 0. So that's a critical point at 0. So x equals 0, critical point. Not a stationary point. The derivative doesn't equal 0. Okay, we should see what's going on. And by the way, let's check the endpoints. So the way you'll see this done in the BC exam, when this is a free response question, is something like this. So they'll be like, well, check the endpoints, -2, 0, 3. I don't do it this way almost ever, but I thought I'd just show it to you. And then it'll say, what's f of x? Plug in 0, we get 0, plug in -2. Well, that means -2 squared is 4 3rd root. So we get the 3rd root of 4, which I really should get a decimal for. And then plug in 3, well, that's 9, is the 3rd root of 9, if I'm not mistaken. About 2.08. 3rd root of 4 is going to bust out the calculator. Four to the 1 divided by 3. A lot of people are freaked by that. Sorry. There you go, 4 to 1/3. We could also do math. Go down, hit the third root. Sorry for the reflections. Enter. Let's start doing this on my calculator. Oh, look at that, same thing. So either 1/3 power or third root. They both work. So it's like 1.587. I really should go to 3 decimals. I mean, I could tell from the graph, but hey, it's never a bad idea to check here. Actually, I feel really bad about not going 2.80. I get it. Oh, that's why I didn't. 3 decimals. Oh, we should go 3 decimals. So this is a, we don't care about the locals. So we're just looking at a global, no, absolute min. That's nothing, and that's an absolute max. Something like that. All right. Now I cheated putting the graph up first, which is never a bad idea. Let's try again with the derivative. F prime of x equals, well, that's a little too hard for me, so I have to write this as 4 minus x squared to the negative 1/2. So that's negative 1/2. 4 minus x squared to the negative 3/2 times negative 2x. Cancel, 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 cancel. Equals x over 4 minus x squared to the 3/2. Now you will find that we often just care what's going on the top. So to make this equal to 0, we know it's just x equals 0. And let's double check on the bottom. That doesn't cause problems. Now we could also find a critical point on the bottom. It looks like plus or minus 2. But we can't actually put those in because that's going to cause undefined. So we should probably see what's going on. Check x equals negative 2 question mark, just because they're kind of points of interest, what we call critical points. So I'm going to use my calculator to do this my computer to do this because my calculator doesn't show up worth a darn. Let's graph it, see if we can figure out what's going on. Got to get myself out of parametric here. Cannot possibly over recommend this. Alpha y equals 1 over square root 4 minus x squared. Graph it. Very cool. Now you might be like, well, there's your maxes. Yeah, not really. Oh, goodness gracious. I don't think I shared this. Sorry about that. Share screen, calculator. Let's show you what I did. Sorry about that. So y equals 1 over square root of 4 minus x squared. And then I graphed it. I got this. And you might say maxes and a min. Yay, we do know what we're doing. Stop share. So we've got this kind of funky graph here. All right. And actually, let me back up a step. At x equals 0, we have an absolute min of 0. When they find the max and min values, we have to think about at x, at f. All right. What is the global max? It's 2.080, third root of 9. Where does it occur? At x equals 3. More on that later. So find the extreme values. So negative 2 and 2, they're not in the domain. So again, our calculator steered us wrong. This is what the calculator just graphed. Hey, I thought we could always find a max. If we go back a page and read it, it says we can find a max if it's a closed domain. This is not closed. So we're not allowed to check negative 2 and 2. So we end up just saying we have an absolute min at x equals 0 of plug in 0, 1 over square root 1/2. Important, 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 get that. And then, oh yeah, by the way, there's no absolute max. Why does that bother people? What happens at the 0 for the graph y equals x to the third? Not quite something completely different, but now for something almost different. No max or min there. But wait a minute, when I go y prime, I get 3x squared, y prime equals 0, x equals 0. This is why we have to always check. We don't just graph and say done. We look and we figure things out. We go from there. All right, I cheated by looking at the graph. What we would normally do is say what's going on at 0. We would say, okay, plug in a number above 0. Plug in 1. 4 minus 1 is 3. Square root of 3 is positive. That's positive. So positive. Let's plug in -1. Oh, wait, I'm plugging into the wrong spot. I got to plug it into the derivative. Plug in 1, we still get positive. Plug in -1, this is always positive, so we get negative. So look, it's a min. Well, let's go down here. We use the derivative to do this. Apologize for all the confusion. 0, plug it into here. Plug in 1. All right, 1 squared, we get a positive. Oh, it's going to be a min. Plug in -1. Also get a positive. All right. So this is called a point of inflection. Talk more about how to find it in a second. Basically, we take the second derivative, but we'll get to that in a minute. So what's going on there? We'll check it out. Concave, curvy, circle-y, down. Concave, bendy, circle-y, up. I do it with the fingers. Concave up. Get my finger in there. Concave down. Got 2 of them doing this. All right. More on that in a minute. That's what a point of inflection means. When the slope, here's how I always thought of it. The slope is now positive, but it's getting more and more and more negative. It's going down. It's 100, 50, 1, 0.1, 0. It's almost 0. And then it changes its mind and goes the other way. Now it's becoming more and more positive. So it's where the slope changes direction in its future. Well, that's really horrible, but hey, it's tough. Deal with it. So keeping things moving along here. Find the extreme values of, oh no, it's a piecewise. Definitely have to graph this. At x equals 1, 1 plus 2 is 3. And that's greater than 1. It's x plus 2, so it's basically doing that. And it's forever. No closed interval here. 1, 5 minus 2 is 3. It's an upside down parabola. Plug in 0, I get 5. 1, 2, 3, 4, 5. So this is something like this. So we cannot do this without looking at the graph. It's impossible. We can do this side. Hey, it looks like there's a max there. Let's see what's going on. So f prime of 0. See what's going on there. Should be, that's not what we want to do. F prime of x when x is less than 1 equals, see ya, -4x. -4x equals 0. X equals 0. Plug it into here. Plug in 1, I get a negative. Plug in -1, I get a positive. Right, so that's going to be a max. And we can just look at the max and do it, but I'll look at the graph and do it, but we're trying to do this right. Yes, by looking at the graph, we know that. So we have a local max of, I did this differently before, I'm doing this on purpose, of 5 at x equals 0. Local min of 3 at x equals 1. And that's just from what we call inspection, looking at the graph. All right. One more. No calculator allowed. All right, let's see if we can figure out what's going on. F prime of x equals 1 over x over 1 plus x squared times the derivative of this thing. Oh, this is gonna make me insane. I gotta think about this now. Derivative, it's low plus x squared d high, 1 minus high, x d low, 2x over 1 plus x squared squared. Oh, well, I can cancel that and that. Equals 1 over x times x squared minus, careful, x squared minus 2x squared is -1 minus x squared over 1 plus x squared equals 1 minus x squared over x times 1 plus x squared. Now, I have to set this equal to 0. Don't care about the bottom as long as I don't plug in a 0 and kill it. So I just care about the top. So 1 minus x squared. What in the world? 1 minus x squared equals 0. 1 equals x squared. Square root. X equals plus or minus 1. Number line them, use the derivative. -1, 1. And this is where we're plugging it in. Can't use 0, it'll kill us. So we go with 1/2. Now we don't really care about the results. 1/2, the top's going to be positive. 1/2, positive, positive. So 1/2, we've got this positive slope. I got a critical point here. I have to look at the original graph, find out if there's a critical point. So I'm going to go with 1/2 here. There's a critical point at 0 because I can't take the natural log of 0. So that's going to be a infinite asymptote. So let's put in -1/2. Yay. -1/2 into here. Top is positive, positive, negative. So we got downward slope here, positive, negative. Plug in -3/2. Interesting. Let's go with -2. That's a lot easier. Squared is negative on top. Negative over negative is positive. This is always positive. Positive. Let's plug in 2. Negative over positive, positive, negative. So this graph should do some funky stuff here. All right. There's a max at 1. I'm going to put it here because I know, and a max at -1. It's undefined at 0, so that's a vertical asymptote. And it does that. At which point you say, well, why didn't we just graph it? No, I didn't give you a calculator. You got to be smart. So we're going to go with a absolute max of ln of 1 over ln of 1/2, which is a negative number, so that's why it's down below, at x equals -1 and 1. It's an absolute value, so that's why I can put them both there. And then there is no absolute min. And let's go find out the end of the story. Sorry about that. ln of absolute value. Let's see what we got. Share screen. Math, go over 1, absolute, stick a fraction bar in there. X over 1 plus x squared. This ought to be interesting. Interesting. I thought ln of 1/2 was negative. What if I screwed up? 1 plus x squared. No, it looks good to me. Let's zoom in, see if we do get an asymptote there. 2. Yeah, right there. It definitely bounces. Interesting. I think I can zoom again. Let's see if it's defined there. Second table set. Start at 0 and go up by really small numbers. Let's go up. Did give me a 0. Interesting. I can't take the natural log of 0. Something's very wrong here. Probably me, it usually is. What in the world? X over 1 plus x squared. You've probably been laughing at me the whole time. Good for you. You should laugh at me. Ellen, math. Love it when I can't sort things out, but it's really good to see that everybody makes mistakes. Alpha y equals. And I was able to use my math knowledge to say something's very wrong here instead of just, well, that's what the calculator told me. It's so funny. I was about to go back and check what was going on with LN with the max and mins, because no way that works. Oh boy, I messed up. No, I'm good. Zoom, enter, zoom, 6. There we go. Down it goes. Let's zoom in on that, see if we can see it. Whew, I was nervous for a second there. 2. Seeing it just stops. Let's try and zoom in one more time. It'll show up when we zoom in, but otherwise everybody thinks it just ends there. It does not. Probably should use Desmos for this, but what are you gonna do? There they go. All right. Anyway, that's enough of that nonsense. Not too bad, but yeah, it's kind of tricky. Happy mathing. Good luck.